Thank you, everyone. So thank you, everyone, for being here. So I guess the real topic of this talk is what am I doing, or what our group is doing. But basically, the main message that I want to show you today is some new perspectives on classic graph questions, and especially in the area of theory of graph algorithms. Um, so, by the way, two things that I would like to ask. If you can show your video, that would be very helpful to me because I usually like to interact with audience, but it's not needed. And the second thing is I will have some poll from time to time, just in case you can participate. It would be nice. And I have one confession here. I'm not very sure who the audience are completely. So I have something in between, general overview and also something a little bit technical, but the technical part is really, really small. So hopefully that is okay. But of course, I just want this talk to be a starter, just in case you are curious about something that I am doing, you can just contact me. All right. So this talk will be about our progress on two frontiers in the field of theory of graph algorithms. Okay. Um, and as I said, I'm not so sure who the audience, so let me start from something very basic. What is algorithms? I'm pretty sure most of you or all of you know already. So just in case. So I think that the short way to think about algorithm is just that it's a formulas. You can think of, a mathematical formulas, right? Or some long formulas that you use to tell the machine what to do when it is asked to do something. So we can say it has to do some tasks or it has to solve some problems. And this is pretty much what you can find in all the devices that you are using these days. Your laptop, of course, your phone, maybe if you have this cleaning robot at home, or maybe your smartwatch, for example. Okay, and the algorithms research, which is the area that I'm in, we just ask this question: how smart can computers solve problems, right? So we just want to try to come up with some new ideas or basic new formulas that allow computers to do things better. And with that, hopefully, with smarter algorithms or these smarter formulas, we can process bigger, more complicated data, for example, and hopefully we will use less of hardware, time, energy, right? Maybe you don't have to upgrade your computer too often if you have smarter algorithms. Or maybe if you upgrade your computers at the same time when you have smarter algorithms, then together you will get even better performance, for example. And I should distinguish also between the two sides of research on algorithms, theories and experiments. So the theories, which is going to be the focus of this talk and my work, we focus on mathematical modeling of computers, and we try to prove that something works. And one principle that we try to do is we try to have principal performance guarantees for all the inputs. In some sense, we don't want something unexpected like a black swan, like some input that we haven't thought of and it didn't work. We didn't want that. We want to prove that the algorithm works for all the inputs. And on the other side, there is some experiments, right? I guess many of you are doing this too, which you want to measure performance on existing data on different parameters. For example, in this graph is actually from one of my paper, although it's not my main thing, but sometimes I did this. So my co-authors run these experiments and we have tons of data and we have our algorithms with different parameters and we want to measure the performance. So the y-axis is the performance and the x is just the size of the data on different data. And you just want to see what happens, right? So I'm sure most of you know better than me on this. But again, today, I'm just going to focus on the theory side. I think there are pros and cons on both sides. And so a remark and a question for you. So this talk is again about theoretical works. I will not mention experiments again, but I would love to learn about I don't know, relevant applications, relevant experiments from you. Okay. Okay, now that I'm done with what it means by algorithm, let me also tell you, just to be sure again, graph. So I claim that graph or network is everywhere. And just in case, here's the graph, right? It's basically the data about connections. And we just have two things in graph, nodes or vertices, like this circle here, and the edges here that connects the nodes together. Okay, that's pretty much what graph is. And maybe you have seen this kind of data somewhere. For example, if you use your phone to find direction, right? That's basically you are solving a problem called shortest path in on the map, and that's one graph algorithms. Or maybe you have seen something called cut, where you have to cluster graph data. So in some of the algorithm for shortest path itself, you have to do some clustering too. And the cut algorithm is a basic of clustering. And another example is a matching problem. I'm not sure you have heard of this. So imagine, for example, that there are two kind of people, people who want to donate their kidney and people who want to receive. But it's not that everyone can receive the kidney from everyone else. So now you have like the connection between people who can match, right? And you want to match the pair so that you have as many people that can receive the kidneys. All right, so that's the matching problem. And you can imagine that there are more. And again, I love to hear examples from your side too. So now, and if you have a background in computer science, hopefully you agree with me that graph algorithms, the theory of graph algorithm is a basics, is a foundation of this field. So first of all, they have tons of applications, as I mentioned before. So this is the new picture, but again, this is some example of cut algorithms. And these algorithms, there are many libraries that are devoted for just graph data or graph algorithms like Network X, iGraph, and so on. And another thing is, if you did your undergrad in computer science, you probably have seen some of these algorithms. So now let me read some of these out loud and just state the running time, just so that it reminds you of some of the basics. Um, And if you don't understand this, don't worry. Okay. So shortest path, you probably remember Dijkstra algorithm, and its running time is m plus n log n, where m is number of edges, n is number of vertices. Again, just a quick reminder: edges are these connections, and the vertices are the dots, right? Minimum spanning tree, you might remember Prim, Kruskal, or Borufka. Meshing, you probably have heard of hop, crop, and carve. And min cut, you probably have heard of Carger, especially if I don't know any of you went to my course. So if you went to my course, you probably have heard of this. Um, so all that said, I guess I have convinced you that this is an important area. Um, the problem is that this area has been studied for a long time, but there are still many frontiers. And I'm going to mention two major research frontiers in this field of theory of graph algorithms. So the first frontier is called fast sequential algorithms. So what do I mean? Ideally, we want to solve all the problems as fast as possible. And the golden standard in the field of graph algorithm is called linear time, meaning that you want to get the running time that is as fast as reading the input. Okay. And the problem is that many problems still require quadratic, which is higher than linear, or cubic, or even more time. So let me give you some example. Oh, and by the way, now I'm gonna do some polling from time to time. So let me learn about you a little bit. So Jana, can you create a poll? And my question to you is, are you comfortable with the notion of big O notation and time complexity, as you see in the middle column here? So the answer is yes and no and maybe. And Jana, I don't see the result, so probably you have to read it out for me. Ah, I see the chat result now. Thank you. So yes, great. All right then.
May I throw in
95%.
something? Is it
Yes,
okay to interrupt?
yes.
Jana, is it okay to ask questions during the talk, or should we wait until the end?
I think you need to ask Danupon that.
It's okay for me if you are okay with having your voice on the recorded video.
Okay. Yeah. I mean, there are also many applications like routing where we are definitely interested in sublinear algorithms, right? Is this a principal difference from what you say, or you just decide to cut
Well,
off
you
at
will
linear?
see the word sublinear a few times. So
Okay.
I think, okay, one point that I'm trying to make in this talk is actually sublinear algorithm is one thing that we should think a lot more and more and more in the future. So, so but the point is that for many problems, you cannot actually hope to get sublinear time, meaning that you, so what is sublinear, right? You don't even read the whole input. So for most of the problems, you cannot really hope that unless you are sacrificing something. For example, you want approximation result instead of exact result, or you have tons of time to prepare your data before you actually go and doing some tasks. Okay, yeah. So that will be actually a little bit related to, frontier number two, by the way. So thanks for the question, and hope there's more questions. I'm very happy if people ask questions. So, okay, so, but let me now just, again, just to make sure that you understand this notion, right? So I'm going to mention this a few times. So the golden standard is linear time. This is the best possible for most problems, maybe not all. And just to give you some example, I think, so let's say you have 10 million vertices and edges, and usually the time that you need to read the input is probably order of 10 milliseconds, depending on your machine, I guess, your hardware. Um, and the linear time algorithm is probably takes a bit more, like maybe 6, 7 times more, because you have to do something else besides reading the input. Now, for some of the problems, one of them is Vertex Connectivity, which I'm gonna go into a little bit more. So if you don't know what it is, don't worry. But basically, the best running time with the fine print that before the word that I'm gonna mention soon is something called quadratic, which is n squared, where n is the number of vertices. And if you just compute, right, this is what is n here? N is what 10 million. So 10 million of 10 milliseconds, that becomes about 2.5 hours. So to solve the same problem, now if you don't have linear time, then instead of 10 milliseconds, then you get 2.5 hours. And if you want to solve all pairs shortest path, which means you want to know, how to go from one city to another for all the cities in the world, for example, then the best running time we have is cubic time, which is n cube. And if you multiply these 2.5 hours by another 10 million, then that's roughly 3,000 years. So with bigger and bigger data, and Facebook account, we have 3 billion accounts, right? And the number of people in the world, I think, is 7 billions, I think. We even reached there yet with this computation. So we probably want to do something to get the running time here faster. All right. And this is actually the pretty well-known frontier. People have thought about this for 50, 60 years. So in this talk, I'm just going to tell you something a little bit new about this. So the second frontier is that also modern computers need modern algorithms. So what do I mean by this? So if you think of the algorithms that I have mentioned in the beginning, or the algorithms that you have seen in textbooks, they are pretty classic, and they are invented in classic paradigms. What do I mean? They were invented at the time where we have single computer and small static data. So here's some examples. So the point that I want to make again is that many standard textbook algorithms were invented in this era where, for example, Dijkstra was in 56 for shortest paths. Tarjan and Hopcroft-Tarjan for connectivity was in the 70s, and Hopcroft-Karp from matching is again in the early 70s. And the machine, in the 70s looked like this. But today, we have new paradigms, many new paradigms. The data is different. It's big, it's evolving, and we probably store the data in many places. And the device also different. So we have distributed computing where we have many machines that help each other to to compute something. We have multi-core computation, and we have some low memory machines, for example, your phone, or maybe some sensors. Okay, and we don't even know how the future looks like, right? Maybe we have quantum computers, and we have AI that might help you to do something better, but maybe not everything. Okay, so the point here is that these different kind of computation motivate different models of computation. And still, the best thing we know about algorithms is in this paradigm where we have one computer and small static data. Okay, and these two frontiers together lead me to this research that I have been trying to pursue for a few years. So I call this, in short, it's called multi-paradigm graph algorithmic techniques. So what does it mean? The ultimate goal is to have techniques, again, mathematical techniques that works across many models of computation. Um, I will give you some example later, but just in case you know what Barufka's algorithm is for minimum spanning tree. I guess if you have studied anything about parallel algorithms or distributed computing, you probably have heard of Barufka's algorithm, maybe in some other disguise. So, and basically we want this kind of, I think a Barucha algorithm is one example that works in many models of computation. And my goal is to pursue more algorithms like this. And so in short, I want the techniques or algorithms that fits most of the models. One size fits most, okay? And here's is some example in case you haven't seen any models of computation at all. So distributed network, right? So you have many computers connected to each other, and each computer has some partial information about your data, and still they want to compute, I don't know, minimum spanning tree, connectivity, or anything about your graph. Another example is dynamic algorithms, which is another field that I work on a lot. Um, just imagine that you have social network, right? And maybe 10 years ago, the social network is this small and people don't know each other so much. But maybe 10 years later, people make friends a lot, or people unfriend from other people, or people leave the network. People join the network. So the network changed a lot. The question is, how can you track track some properties of the network? One major open problem in this field is called graph connectivity, which is just how can you know whether the graph is still connected when the graph keep changing, when some edges leave the network or some edge join the network? Okay. And the other example is data stream, where you have a graph stored in the hard disk, for example, and you want to access the hard disk, but you don't have enough RAM, for example, to read to remember the whole graph. And the best way to one way, not maybe not the best, but one simple way to access the hard disk is to read sequentially, one by one, right? And once you finish the whole thing, you can go back to starting point. And this is some model called multi-path streaming algorithms. I will come back to this a bit more in the example that I will give later. But this is just to give you some flavor that there are many models of computation. And for most problems, we don't actually have a very good solution for even the very basic problems like cut or connectivity. Um, and why, what is the benefit of this? I think there are at least two benefits of this kind of research. First of all, the short-term benefits is that when we try to study the same problem in many models of computation at the same time, then we probably have a better chance to get new insights that may emerge naturally from one viewpoint or another viewpoint that we need the right model to think about. And in the long term, maybe we will have a long-lasting algorithms and techniques because we have the model, we have algorithms or techniques that work well in most of the paradigms that we know of today. And maybe for future paradigms, they are not too different from the existing ones. And maybe our algorithms can be adapted to that. All right, so that's the benefit. But um, that's probably not convincing, right? So maybe let me just tell you what we achieved so far. Hopefully that is more convincing that this kind of research methodology actually works. At least it works so far. So here are some of the results that we have achieved so far. Um, First, if you care about improving some long-standing questions, so here are some examples of what we could achieve. So the first problem is called vertex connectivity, which I will talk about a little bit more later. So we have achievement over 50 years. So the best running time for this problem dates back 50 years ago, and now we could get something better. Another problem is called dynamic connectivity, where again, you want to just maintain whether the graph is connected. Very simple problem, right? Except that now the graph keeps changing. And there is a major open problem in this field, which is called dynamic connectivity. And we just recently resolved this major open problem. And the other problem is bipartite matching problem, which again, this kidney donation setting that I have mentioned in the beginning. Again, we have the first improvement in 49 years for this problem. And mean cut, again, for this problem, I will revisit this again. So again, we have a little bit of improvement in the sequential setting uh, in 20 years, but beyond that, our algorithm actually works in many models. And also another problem called dynamic shortest path. Again, 30-year first improvement in 30 year. And a bit of more comments about this just in case. Again, I don't have time to talk about all this in more details, but just in case you are curious, feel free to contact me and I'm happy to talk. So this algorithm is actually pretty simple and it was already taught in an undergrad course in the US already. Um, the first, the second and third results, they're actually based on some powerful tools about clustering called expander clustering. So if you know what expander is, this is pretty much a fast way to cluster expanders cluster the graph into expanders. If you think this kind of clustering might be useful in your work, please let me know. So far, it has quite a few applications in the theory of graph algorithms already beyond what we achieved here. So people have extended to some static algorithms, some people extended to distributed algorithm, and some people extended to dynamic algorithms. Some of my co-authors kind of say that um, this year seems to be the year of expander clustering. So, and the last two results, these are example of model universal or multi-paradigms techniques where we have efficient algorithms in many settings. And again, I'm going to revisit this min cut algorithm a little bit more to make the point what I mean by model universal. Okay. And the last point that I want to make is that one, if you are not interested in, like all these numbers, all these long-standing open problems, then one conceptual lessons that I think we should understand more and more is something called sublinear algorithms that Dilian has mentioned. So basically, if I can take a time machine and go back 10 or 20 years ago, I probably tell myself or some researchers at the time that, just don't read the whole input. And hopefully they can probably achieve the results that I mentioned above, maybe 10 years earlier than what we could achieve here. And I will mention a few techniques on the way, but since this is going to be a bit technical, so I'm just going to mention these techniques very quickly. So my plan in the rest of the talk is just to tell you two examples. But before that, maybe it's good time to ask questions if you have any. I guess not. All right. So I will talk about two examples that I have mentioned here. So the first problem is called vertex connectivity. So let me define the problem first, and then I will ask you whether you have heard of this before, because it sounds pretty simple. So here is the problem. So you have a graph, right? And you want to, you have some k, and k denotes the minimum number of nodes that you have to remove, node or vertices, right? That you have to disconnect, that you have to remove to disconnect the input graph. Let me give you some example. So in these two graphs, you just imagine that you have the computers that connect to each other, right? And you want to make, you are maybe some attacker, some hacker. You want to destroy the network. So you want to maybe shut down one computer and make sure that some computers cannot talk to each other. And in this very simple star graph or star topology, then if you just destroy the middle node here, middle computer, right? Then you will see that the computer on the top and computers in the bottom cannot talk to each other anymore. Okay, so this in this case k equals 1. Now, if you have this ring topology or ring network instead, then you will see that you need to remove at least two computers or two nodes, two vertices. And in that case, for example, if you remove these two, then this node get disconnected. So k equals 2 in this case. And in this more complicated case, this is called Peterson graph, by the way. You need at least 3. And in this case, k is 3. And the goal is just to computing this k. Um, how many nodes you have to remove to disconnect the graph? Um, that sounds pretty simple, I hope. So can I ask you now, so uh, time for the poll. Have you heard of this problem? Let me ask that simple problem. Have you heard of this problem or seen something related in your work, your research, and so on? And Yana, you have to share the results. Ah, yes, okay, 85%. So Yana, can you relaunch one more time? Um, do you know how to solve this problem in linear time or near linear or something close to linear for k equals 2, let's say. Again, can you share the result, please? Thank you. So, okay. Oh, okay. Now 6%, right? But I guess for k equals 1, I didn't ask that because this is actually kind of an exercise when you learn depth first search or breadth first search. So at least for k equals 1, that should be easy if you just take a few minutes to think about if you remember what depth first search is. So let me tell you a little bit about the history of this problem. So people ask this for a long time. How fast can you compute k? Okay, and for the case of k equals 1, um, this was known since 71 by uh, Tarjan. Probably you have heard of him, Turing Award winner. He could get a best possible result, and that's pretty much using depth first search. You can find this question in this textbook, for example. Okay. Now for k equals 2, it just took a few years later. Um, Again, you can solve the problem with best possible running time, which is linear, or m. Again, m is the number of edges in the graph. And this is used due to the technique called SPQR3. It took now two Turing Award winners, Hopcroft and Tarjan, to figure this out. And this is a bit more complicated. I'm not sure you could find this in textbooks, but you can find it supported in graph libraries. Okay. Now for k equals 3, then for this, you actually have to go back a few years before Tarjan and Hopcroft. So this is due to Kleitman, but the best running time now is not linear anymore. It's n square, what I call quadratic. And as I made the point before, think of the graph with 10 million nodes, right? This could be 10 millionth time slower. So it could be, if the linear time takes 1 millisecond, maybe this takes 2.5 hours. Okay. And in fact, this is the best we know so far. And it was even conjecture in 74, 1 year after Hopcroft got this result with Tarjan, he started to think that, okay, everything should be linear. So he made a conjecture in his book here in 74, 1 year later, that there should be linear time for all k. Okay. It turns out that so far, despite many ideas that people thought about, this quadratic time is still the best you can do for k equals 3. Okay, so I have this list of running time, and this running time, they imply different numbers for different parameter k. But if you just think of k equals 3, then they just boils down to these numbers, n square. Okay, and then again, if you don't understand this, don't worry. My point is that there are many works, but all those works cannot get anything better than n square, where n is the number of nodes in the graph, even for k equals 3. Okay. And now, before I tell you a little bit about what we solve, let me just tell you what we achieve now. So our running time. So again, m is number of edges and n is number of vertices. So we can get pretty much almost best possible. So our running time is m log square n for k equals 3, and not just 3, 4, 5, and any constant actually. Um, this is There's a technical term for this. This is called almost near linear time, and this is actually what most people in my field are happy with already these days. Because there are so many things we don't know we can even achieve this. Okay, and again, just for comparisons, right? So n square time or quadratic time before, it could be 2.5 hours if we think of linear time as 10 milliseconds, and this log square n time here, it's pretty much roughly half a second. So it's not as fast as 10 milliseconds, but it's still more acceptable, I guess. So more generally, our running time is mk square log square n. So for small k, that's okay, but for big k, then we start having a problem. And that is still a question that I am still pursuing these days. For large k, what happened? So the conjecture is you should get almost pretty much the best possible for every k. Okay. And just again to mention, this is the first improvement in 50 years, and it settled the classic conjecture for small k. And it was taught in some undergrad course already. The algorithm is very simple. Just unfortunately, I don't have time to explain to you the whole algorithms. And just as I said, there are theory and experiments. So this is just one of the few works that I managed to have some experiments already. Question? Yes.
Uh, is it the best that has been achieved so far, or you have proved that this is the optimum?
Oh, you mean like I eliminate this log square, for example? Is that what you mean?
I don't
Yeah,
know.
or like this k. No, so there's a few. Okay, thanks for the
Have
questions.
have you proved that OM is not possible?
Oh, okay, sorry. Yes, when I say best possible, sorry, I mislead that. It's almost best possible because it's still possible that you get OM actually. So no, we don't have a proof, and it's pretty hard to prove anything in this field. So people have, again, there's another sub area in this theory of graph algorithm called fine grained complexity, where people try to prove lower bounds, and they have to make some assumptions, but not for this problem. That we don't know. Okay, and that's another field that if you're interested, just feel free to talk to me. Fine grained complexity. And again, this is just a quick result. So the red one here is just the previous base result, and this is what we could achieve with just implementing our algorithm. And if you add heuristic, then it's even improved faster. And I think you can see this is 100 of I don't know, I don't know if it's 100 times, but it's much faster. And this is just for the graph of about 250k vertices. We didn't get to do 10 million vertices just because it will take forever for this red line to compute. So we just cannot compare with that running time. Okay, and this is still a work in progress that someone is still doing experiment here. Um, Now I'm just gonna spend a few minutes talking about the ideas, but any question? Because now it's gonna get technical.
I have
Yes.
one question. So you mentioned that, I mean, I'm not really work on this, but I was curious about the general insight, which was you don't read the entire input. And I was curious whether you give some insights on how you manage to get this, basically to check vertex connectivity without checking the entire graph. Like
Okay, I
a
see.
simple intuition.
Right. I hope what I'm gonna say in the next two slides may shed some light. So when I say this is, it's not that in the end we're not gonna read the whole graph. We're gonna do, but in between that we will define some sub-problems that we're not gonna read. That sub-problem itself doesn't need to read the whole graph. So you probably see that in the next two slides. Hopefully I make some point there. Yes, and the key idea is again, it's going to be some problem or algorithm called sublinear vertex connectivity. And the point that I want to make here is that this, if any of you work in distributed computing, you probably have seen kind of something similar to this in distributed computing. So to me, it seems like an idea that natural in distributed computing, but now we kind of it turns out that it is useful in sequential setting as well. And this is probably not something that people 20 years ago think of these techniques too much. Okay, so, and if you cannot understand the next two slides, don't worry, it's a bit technical, but it's hopefully not too much. So I have to define a problem. Actually, just one slide here. So the problem is this. I'm given a graph G and I'm giving some parameter K, right? Which basically I want to know if I can delete K vertices to disconnect the graph. And in addition to these parameters, I'm gonna get two more parameters. Some small number P, think of something like, I don't know, root N, for example, and S, which is a node, a vertex. And what you want to output is that you want to know whether you can remove K vertices to split P vertices nearby X. What do we mean by nearby S? From the other vertices. What I mean by this? I want to delete some vertices so that I have two connected components. One of them is small and contain S, and the other is large. Let me give you example below. So the right picture, right? If K is 4 or 3, for example, and S is here, then I can delete this vertex. And let's say K is 1, and sorry, P is 4. And so I can, once I delete this middle vertex here, I'm gonna have something very small here and something very big here. Okay. So again, I'm not interested in the case where you have, like big two components and I have something small in the middle that I can remove. For that, you don't have to find me. But if there is something like these vertices that is pretty near S, then I would like this problem asks you to find this vertex. And this is more of the abstract picture on the left. Okay. And the claim is that you can solve this problem in pk square time. And again, if you think of p as root n and k as 3, for example, then this is just root n time, right? Which means that you don't even have to read the whole graph because the graph has n vertices. Okay. How to solve this problem? If you work on, again, distributed computing or something related, you probably know something like crawling, right? Like you kind of do some local exploration, you kind of grow from S, and after you grow a little bit, you realize that the region that you have explored doesn't have any such vertex, then you just stop. That's the rough idea. And again, I don't have time to explain too much. I have actually slides prepared at the very end. So if you are curious, I can just show you later. Any questions about this? I cannot see if you raise your hand, but so I guess not.
I have a question about the previous problem that you
Yes.
defined. So what's the relation between N and M in your experiments or even in
Ah,
this
I see.
formula?
I see. So usually there is some nice clever algorithm that was dates back maybe 30 years ago that shows that you can assume that M is roughly NK.
Okay, I see.
That's it.
Mhm.
Makes me so.
Yeah,
And
because
in
otherwise you'd end up with N squared again, right?
yes, right.
Mhm.
And in this example, I just assume that they are pretty much the same, right? M
Mhm.
and N,
Okay, I
right?
see.
So for small k, you can assume already that M is small. But yeah, for some other problems, then you probably have to consider big. And that's why I said I'm still exploring the case where k is large, right? Because in that case, M is much larger than N. And in that case, actually, the best algorithm is not even n squared, it's mn, which is n cubed for m equals n squared.
Oh, I see.
Okay, so it's even much worse.
All right, thanks.
All right, thank you. No other questions? So okay, now let me then yeah, if you I thought Dilian, yes.
Yeah, maybe I missed a point. Do we assume that we know the topology?
No, we don't.
No, okay.
No.
Because this changes, right? If, for example, for the star topology, if I know that it is a star, then the algorithm must be extremely quick, right? I have just one neighbor at most.
Right.
Yeah.
Exactly. You don't know anything about the topology.
Yeah.
Yes. Okay. If you kind of get lost somewhere, this is maybe another problem that you can have a look. And again, if you find something related to you, please let me know. Minimum cut. Okay, let me define the problem again and then ask you if you have seen the problem and some algorithms, right? So, an official name of this is a global minimum cut problem. So it's similar to the previous one, but now you want to remove edges instead of vertices. And now the graph has even weights. So the goal is, again, you want to remove edges to disconnect the graph, and you want to minimize the total weights. For example, here, if you remove these edges here, then I have the weights of 4, 6, 9, 10. So the cut value is 10. And then I disconnect the graph into two sides, right? And you probably, as I mentioned, this is kind of a primitive, at least what people told me, in data clustering and in graph clustering and in image segmentation. And if you know of other applications, let me know. Um, now let me ask you two questions again. The first question is, have you seen this problem before? Yana, please. Can you share the result, please? Thank you. Yes, great. 95% of you say yes. 94. Now the next question is, um, do you know how to solve this problem, let's say in quadratic time instead of near linear time? Quadratic means n square. Can you share the result again, please, Yana? Around 30% of you say yes, and 30 is maybe, and then the rest no. All right. So I'm not sure if it means that 30% of you went to my course, or maybe you have seen it from somewhere else. So actually, this problem actually can be solved in what we call, again, near linear time, m log cube n. But let me just remind you. So in case you have been to some advanced algorithms course, I'm pretty sure you have seen this algorithm. It's called Karger's algorithm, and it takes roughly quadratic. Again, we have some extra log square, but again, people in my field right now, we don't care too much about log now, just because there are many other terms, right? Except that now, when we get to m log cube, then we start to care more, okay? So you probably have seen this algorithm that takes quadratic time. And maybe just to ring more bells, it's called random contraction. Where the algorithm is very simple. You pick some edge, you you put the two nodes on the two endpoints together as one node, as one node, and then you pick another random edge. So you keep picking random edge until you have two nodes left, and whatever you have left, you just cut it. So that's pretty much the whole algorithm. Okay. So Karger went on to get nearly linear time algorithm. This is one of his most celebrated results. And you probably have seen this in some books. For example, this book is this one of the first example of randomized algorithms. And the problem with this Karger's algorithm that is nearly linear time is that it's quite complicated. It involves dynamic programming and some quite involved data structures. And as a result, there are two problems with it. The first one is that it's hard to adapt to new computational models. And as I have made the point in the beginning, probably in our new computing paradigms, we need new computing models. So, and in particular, we don't have efficient algorithms in distributed streaming and many other settings. And also, it is expected it is slow in practice. So I'm just going to quote the paper co-authored by Carter a year later. So he said that this algorithm is more complicated and the constant factors of its implementations are likely to be large. So they are not implementing this algorithm. And as far as I know, nobody has implemented these algorithms. Okay. So although we have this very fast algorithm here, I think the algorithms that got implemented and used a lot these days is this quadratic algorithm, which to me is quite unfortunate. Okay, so and let me give you some example of the first point, the computing paradigm, right, or model of computation. Uh, this is an example of a graph stream. So think of the following: you have a big graph in the hard disk, right? And it's stored this way, like you have one edge and then another edge that's connect 2 and 4, and then another edge. Let's say you have an edge between 1 and 3 and so on. And you have a pretty small RAM. And usually what people assume is that you have just ON memory, where while the graph could be much larger, right? It could be N square memory size of the graph. And what you do is that you read the whole graph, you read the edges one by one until the end. This is called the first pass. And of course, you cannot remember the whole graph. So now you probably want to go back to the beginning and read again, okay? And that is called the second pass, and you can do it again and again and again. And the question is, how many passes do you have to read the hard disk in order to compute something like this minimum cut problem, for example? And the goal is you want to minimize the number of passes. Any question about the model? And if you don't understand this fully, don't worry. I'm just giving you, a flavor of the model that people have thought about. Okay, so if there's no question about the model,
I just ask,
yes,
you said that you're reading them one by one.
right.
Would it be a different problem if you would say that you're reading them in chunks?
Block, right?
Yeah.
Yes. So if you still have to read sequentially like this, then I don't think there's any difference. But then there is another model called external memory model, where you can, I guess you know better than me, like you read some block somewhere and then you read another block, right? So again, that one, we don't understand it so much as well. And what I'm gonna talk today, I'm not gonna touch that just because it's a bit more complicated. All right. But yes, that's one very valid model. All right. Any other questions? Thanks for the questions, by the way. All right. So, and here's the issue of streaming min cut problem. So we actually have some algorithms that work pretty well in this model, except that existing non-trivial algorithm works on something called simple graph. If you don't know what simple graph means, it means that you cannot put weight on the edge. And second, you cannot have parallel edges. What do I mean by this? Between two vertices, I cannot have two edges like this. Okay. And again, I cannot have weights. I cannot put number. So this graph, for example, is not simple because I have two edges between the same vertices. And this graph here is not simple because I have weights on the edges. Okay. The existing algorithm, we have pretty good algorithm that just require two passes, and they were discovered just a few years ago. But as I said, it doesn't work on non-simple graph. And actually, this is a common barrier in many settings, not just streaming algorithms. So there have been quite a few developments in the past few years, but the problem is that new results that we have seen in the past few years, they don't work, they work for simple graph only. So let me now tell you a little bit more these tables. So sequential setting, there are these improvement in 17 and 20 that improve over this Karger's classic result by some log factors, but they have to assume that the input graph is simple. And now let's move on, and this is the model that we have thought about a lot, like sequential setting. Now, if you move on to modern model for computations, like streaming algorithms, distributed algorithms, and something called cut query, as I said, streaming, in terms of number of passes, we know that we have 2 passes, but for non-simple graph, we just have n, and this is pretty trivial algorithm, actually. And in distributed algorithms, I have to define something called time complexity or rows in distributed algorithms, but I don't have time for that. We know that the best you can do is root n, where n is the number of nodes. But the best you can do is n to 0.9, and that you have to assume that the graph is simple. And for and otherwise, we just have trivial algorithm that takes n square. And then another one is cut query, which I think I'm not going to touch all of that. So now what we could get, again, any question about previous work, by the way? So if not, then what we could achieve is that we could get, first of all, so our focus is on modern model of computation. And what we could get is we could get log n passes for the stream. So this is probably the best you can get, but it's at least it's much better than n. Okay, and in the distributed setting, now we have root n running time, and this is tight when you look at this lower bound here, and it's even improved the previous result that assumed that the graph is simple. Okay, so by looking at these many models at the same time, we can get an improvement over many models already, and we can actually improve even the classic result by Karger from 20 years ago. Again, this now we just improved by a log factor. So from n log square to from n log cube to n log square, and there is some follow-up work now that get n log already. So we are pretty close to linear time, the golden standard for sequential setting. And again, the point that I want to make here is that by looking at other models, you actually get to see new perspective for the classic model of computation, and you get some improvement in that model too. And again, I'm just gonna end this talk by just tell you just some ideas, actually some puzzle that is the key subroutine in this problem, and it's again sublinear algorithm. But any question before that? So if not, so here's the puzzle. And I think if you are pretty good at algorithms, you probably can come up with the solution in 2 minutes. So my youngest student who just joined a few months ago, he could solve this in, I think, 20 seconds. So let's see. So here's the problem. It's called matrix mean entry problem. Okay. So I have this input. So think of the following game. I'm gonna write down a matrix, and it's m times m matrix. Okay. I'm gonna write this down on my notes. Okay. So you don't see that. I'm write down in my note of paper, but you know what n is. So you know the dimension of the matrix. Okay. And then I promise you one thing, that the matrix that I write down has this property called monotonicity, where the columns minimums never move up as we go to the right. What do I mean by this? Let's look at this example on the right, right? On each column, I square the minimum. Okay, this is the minimum of each column in the boxes in this square. And now you can see that if I move from the left to right columns, the square never go up, right? It keeps moving down or stay on the same row. Okay, this I promise you that what I wrote down in my book has this property. Okay, now you can ask me this. Uh, First of all, you want to the goal that you have to do is to find the minimum entry within my matrix. Okay, and what you can ask me is you can ask for one entry at a time. That's all you can do. Okay, you can ask me, what is the number on the leftmost upper left of the matrix, for example. Okay, you can point to one entry and ask me the number on that entry. The question is, how many entries do you need to solve this problem? Okay, so I'm not gonna spoil the fun. So again, if you are curious about the how to solve this, you can have a look at these slides later. I guess maybe we will have some video or some slides share to you later. Okay. So let me just jump to the solution. But let me give you a hint actually that you don't have to ask for the whole matrix. You don't have to ask for the n square. And that's why we are talking about sublinear algorithm. And this has a connection to min cut. The connection itself is a bit surprising, but um, again, I don't have time to explain that connection. I probably need like 10 to 15 more minutes for that. All right. Okay, now any question before I conclude about the min cut problem and everything? So conclusion is I have talked about two frontiers in theory of graph algorithms. The first one is just the fast algorithms in the classic setting, sequential setting. And the other one is this lack of fast algorithms on new models of computations. And we have made progress on two frontiers at the same time and by studying many models of computations in parallel. And main technical lessons that I want to emphasize here is this thing called sublinear algorithms. So if you have seen this keyword elsewhere, maybe this is what you should pay attention to or think about a bit. And basically, you just don't read the whole input. And here's the question for you. Can graph algorithms and techniques, and especially sublinear algorithms, be useful to your areas in your applications and so on? And if you feel so, please let me know. I'm very interested to know that. So that's all. I have, and I was told to finish before 4, and I think this is 2 minutes before 4. So thank you, and let me know if you have any other questions.